In this video, I'm going to solve this second order homogeneous differential equation. It has constant coefficients and it also has the initial conditions or given conditions. So the equation is this, and the initial condition is y of 0 is equal to 3 and y prime of 0 is equal to 7. And just to let you know, the characteristic equation will have roots which are complex. So they're going to be complex conjugates of each other. So we'll make the usual assumption. So let's say our equation has a solution of this form, e to the power rt, and then that gives me y prime to be r e to the power rt, and gives me y double prime is equal to r square e to the power rt. If I plug in these values into the differential equation, I get r square minus 2r plus 5 times e to the power rt is equal to 0. So you have two numbers here. Technically, you're multiplying, getting 0. One of them cannot be 0, which is this guy. The exponential function is not going to be equal to 0. That leaves us with not many choices. That has to be 0, which is this one. R square minus 2r plus 5 is equal to 0. So this is a quadratic equation. R square minus 2r plus 5 is equal to 0. My a is 1, b is negative 2, and c is 5. So if I use the quadratic formula, I'm going to get r is equal to negative b plus or minus square root of b square minus 4ac, all of it divided by 2 times a. So my r is going to be negative b, so that means negative times negative 2, because b is negative 2, plus or minus square root of b square, meaning negative 2 whole square, minus 4 times a is 1 and c is 5, all under the square root, divided by 2 times a, 2 times 1, because a is 1. So my r is going to be 2 plus or minus square root of negative 2 whole square is 4, minus 5 times 4, 1 times 4 is 20. All of it divided by 2 times 1 is 2. So it's going to be 2 plus or minus square root of negative 1 times square root of 16. Because square root of negative 16, I could write it as negative 1 square root times square root of 16. All of it divided by 2. And this is nothing but I, right? So my r is going to be 2 plus or minus I times 4 divided by 2. That is going to be 1 plus or minus 2i. So my r1, one solution is going to be 1 plus 2i, and my r2 is going to be the other solution, which is the complex conjugate, which is 1 minus 2i. So technically my solution becomes this. So this is going to be my solution. Y1, so let me write it here. Y1 is equal to e to the power 1 plus 2i times t, and y2 is going to be equal to e to the power 1 minus 2i times t. Now I could simplify each of them. So let's say y1. So let's write it here to save some space. This is going to be e to the power 1 times t, which is e to the power t times e to the power I times 2t. Okay. This, by the way, I could simplify to e to the power t times cosine of 2t plus I times sine of 2t. Okay. This is just the Euler's formula. E to the power I theta is equal to cosine of theta plus I sine theta. Now I could simplify this little further. Y1 is going to be e to the power t times cosine of 2t plus I times e to the power t times sine of 2t. Similarly, for y2, if I simplify it, I'm going to get e to the power t cosine of 2t. Only difference is the sign, minus. It's going to be I e to the power t sine of 2t. Now these two solutions. We can take any linear combination of these two to get the general solution. So that's going to give me y of t or y is equal to c1 y1 plus c2 y2. Now I'm going to make some simple assumption. So let's say in the first case, I assume c1 is equal to c2 is equal to 1/2. If I do that, then I get, let's say, a new solution u of t that is going to be nothing but e to the power t times cosine of 2t. And similarly, if I assume c1 is equal to c2 is equal to 1 over 2 times I, okay, that's going to give me another solution v of t is equal to e to the power t times sine of 2t. Now these two solutions I found u and v, by the way, they are linearly independent. And what you can do, you can find the Wronskian of it. So w of u of t, comma, v of t, and that's going to be nothing but the determinant of, I'm just going to write it out here, u and u prime, and v and v prime. And you can check it. If you take the derivative and do the simplification, you will come up with a number that is not going to be equal to 0. So that tells us that we could write the general solution as y of t is equal to c1 times e to the power t times cosine of 2t plus c2 times e to the power t times sine of 2t. And this c1 and c2 are arbitrary constants, okay? And they are not the same as these ones, this c2 and c1. Now, if we assume the first condition, which is y of 0 is equal to 3, okay, initial condition, so this is going to be 3 is equal to c1 times e to the power 0 is 1, cosine of 2 times 0 is cosine of 0, which is also 1, plus c2 times e to the power 0 is 1, sine of 0, however, sine of 2 times 0 is sine of 0 is 0. So I get c1 is equal to 3. Now I just need to find the derivative and apply the second initial condition. So the y prime of t is going to be this, y prime of t. If you take the derivative and rearrange the terms, is going to be c1 e to the power t times cosine of 2t minus 2 sine of 2t plus c2 e to the power t times 2 cosine of 2t plus sine of 2t. Now, if you just plug in the value, initial condition, which is 7, so that will give me 7 is equal to c1 e to the power 0 is 1, cosine of 0 is 1, and this term is going to vanish. So that's going to give me just c1 plus, similarly, for the second term, c2 is going to be 2c2. Why? c2 is c2, which is a constant, e to the power 0 is 1, cosine of 0 is 1, so that gives you 2, and sine of 0 vanishes. So this gives me 7 is equal to c1 plus 2c2, and if I solve for c2 by plugging in c1 is equal to 3, I get c2 is equal to 2. So I found c1 is equal to 3, c2 is equal to 2. So my general solution is going to be y of t is equal to c1, which is 3 times e to the power t times cosine of 2t. I'm just plugging it in right here. Plus c2, which is 2 e to the power t times sine of 2t. And this should be my solution to this differential equation with the given initial conditions. I hope that this discussion was helpful. Thank you very much.